Hello everyone, I'm Zhenggen Zhong. Today we are going to present our project on reinforcement learning in snake. Learning to control agents directly from high-dimensional vision inputs is currently a hot issue of reinforcement learning. Most successful RL applications used to rely on handcrafted features combined with linear value functions or policy representations, which means the model performance heavily depends on the feature engineering. However, recent development of deep learning has made it possible to extract compressed features from raw vision data. These methods utilize several network architectures like CNN and multivariate perceptual, also benefiting reinforcement learning with vision data. Our project built out a reinforcement learning model with CNN to run successful control policies from video game Snake, which allows players to control a snake growing in length to eat the fruits and avoid obstacles. The network is trained with Q-learning algorithms, and we use experience replay mechanism to train the model based on the previous transitions. In our project, we firstly apply our approach to play snake game on a 10x10 map with and without obstacles respectively. The network was not provided with any game-specific information and was not privy to the internal state of the emulator. It learned only from the vision inputs, the reward, the terminal signals, and the set of possible actions. After that, two modifications have been made. The first one is changing the map with different obstacles, and the other one is using different reward functions. After these trials, we made some comparison about the performance of reinforcement learning models on different snake game scenarios. Finally, we had a discussion of what we have found about snake AI and RL algorithms in this project. Now pass it to Li Zhongxian.
Thank you, Genrong. I will give a brief introduction and some literature review to the techniques used in our project. This section can be divided into three parts: reinforcement learning, Q-learning, and DQN. As a branch of machine learning, the largest feature of RL is learning from interaction. The agent adapts to the environment based on the rewards or punishments. The objective of RL is to get an optimal strategy so that the reward obtained is the largest, where the so-called policy is actually a series of actions. The environment can be formulated as a marker of decision process, as many reinforcement learning algorithms for this context utilizing dynamic programming techniques. The core of the MDP is actually the probability of transition from one state to another state and action A. And the expected value can be calculated by multiplying this probability with the reward of next state. The other important concept of RL is the Bellman equation. The first part of its equation is the immediate reward, and the second part is the discounted value of successor state. When we maximizing these two values, a policy which can maximize the total reward will be given. Q-learning is a value-based algorithm to find the solution for Bellman equation, where Q is the expectation of reward. The main idea of Q-learning is to construct the state and action into a Q table, and then select the action according to the Q value to maximize the reward. However, Q-learning have some weaknesses. Since Q-learning have no predictive ability, it cannot handle new states because it does not have the ability to estimate the value for unseen states. So it is necessary to add another model in Q-learning to predict the Q value. Deep learning is a good choice. However, the challenge is that most deep learning algorithms assume that the data samples to be independent, while in reinforcement learning, one typically encounters sequences of highly correlated states. A paper released by DeepMind shows that a convolutional neural network can overcome these challenges. The structure of this network is shown in the figure 1. The network is trained with a variant of the Q-learning algorithm with stochastic gradient descent to update the weights. In addition, a mechanism called experience replay was used to solve the problems of correlated data and non-stationary distributions. Then I will pass to Wenhui Yang.
Thank you, Zhongxian. So now I will talk about the methodology used in our project. There are mainly three Python files, and I will talk about them one by one. The first one is the string of Python. It mainly has three parts. The first part is the command line parser, which will parse whether you want to train the model or you want to play the model, and what JSON file you want to choose, and how many episodes you want to play. There are also GUI options. With it, you can play the animations, and without it, the speed of training can be much faster. The second part is the model construction, shown on the left. So the input is 10 by 10 of the image size and 4 of last 4 frames. And we have two convolutional layers and one fully connected dense layers. The output is the three actions that we take by the snake. The trained of Python also will pass input parameters to the DQN of Python, like memory, number of last frames, number of episodes, checkpoint frequency, which is 1/4, and it means it will save the model every 5,000 episodes, and the discount factor, which is how the future will affect on the current state. The second Python file is the environment of Python. So the snake will take the actions by calling the game APIs, and we can get the frames of the snake by calling the APIs. We can also generate the fruit whenever a fruit is eaten, and we can know how the game ends, like the snake hits into itself or hits into the wall. We can retrieve initial parameters stored in the JSON. So the JSON will specify how the map looks like, what the reward is, and by default, the fruit reward is set to the snake length, and the time step reward is set to constant 0. And we set the initial snake length to 3 also. And last but not least, it will record the process's result, like time step data, the backlog file, and most importantly, it will save the training or testing results. So every episode, it will save to the CSV. The last file is the dqn.python. And first of all, it has two default parameters. The first one is the exploration range, which starts from 1 and decreases to 0.1. So if the range is equals to 0.1, that means there are 10% the snake will take the random actions, and there are other 90% that the snake will take the action predicted by the current model. And the exploration phase size equals to 0.5, which means after half of all the episodes, the range will decrease to 0.1. And then on the left, you can see the flow chart of the DQN of Python. It mainly responsible for training and saving the model. So first, it will take the action, and then it will save the information like state, action, reward, state, next, game over into the memory. And then from the memory, it will get the random batch and train on this batch itself, and it will understand what the loss of this model is and to improve this model. Last but not least, it will save the model at the checkpoint frequency and print out the training process so that you can trace the performance well. So this is my part, and now I'll pass it to my groupmate.
Thank you, Mr. Wen, and I'm Chen Qinan. I want to talk about the exploration and discussion of our project. It can be divided into three parts, which are the training of our model, testing of the model, and some experiments we do to generate the interesting results. And let's get started. At first, I would like to talk about the map design. We have two different maps, which are the blank JSON, it's like this, and upscale JSON is like this. Because we use JSON file to generate the map, the hash here represents upscales, dot here represents space, and S is the place where the game started. And for showing the training procedure, we need to use the blank map as example. So this is the interface when we do the model training. The criteria that we focus about the performance is first, the total rewards. The training algorithm teach our model to get the maximum of it. And the second, the fruit eaten, which is the score of playing snakes. And exploration here is basically the the probability that the snakes take action randomly, it will keep decreasing from 1 to 0.1, and the probability of taking action based on experience will increase. And we can see the performance here for the fruits and total rewards that is really bad. For the training procedure almost to the end, we can see the performance of fruits and total rewards reach a certain level. Then we can plot a graph of total rewards and fruit eaten. As we can see that both of them keep increasing, so which means that our training algorithm successfully teach our model how to play the game. And then we need to do the testing. In order to find the performance, we played 100 times and plot the fruit eaten. From the graph, we got a mean to reach almost 16. So a snake can reach almost 16 scores in every game. So that's a really good performance. And next, let's jump to the experiment part. As you can see in these two parts, which are the performance of snakes in blank and of scales, when we train models for those two maps, the results in the blank is much better than the results of scales. We know that playing in blank is much easier than playing of scales, so there's a hypothesis that whether the performance of this model trained has negative correlation with difficulties. So we design two more, which named easy, medium, and of scales now become hard. Then we do the testing of them using the same method. But in the graph, we cannot see the difference, so I plot the table. The means of it shows that the performance of snakes does decrease when difficulty increase. For the standard deviation, since the difference is not that large, we treat it as the same. So we prove that the hypothesis is correct. The model this time is just like the human being. And thank you. That's for my presentation. And next, welcome my partner, Mr. Mo.
Thank you, Chinan. Now I will talk about the reward policy. Reward policy plays an important role in reinforcement learning. A good policy results in good performance and vice versa. In this research, we adopted 4 different reward policies. But why did we adopt such policies? Let's check out the video first. The first one is simply do nothing. In this case, the snake will keep self-spinning just like you. The snake couldn't eat any fruit, but it would survive forever. It makes sense because the agent will get punishment if the snake hit a wall or itself. The safest way for the agent to stay alive is self-spinning. In order to avoid self-spinning, we punish the snake for survive. In this situation, the snake will hit the wall as soon as possible without eating any fruits. Survival is meaningless to it. Neither are fruits. The best way is to commit suicide. The third one is to encourage the snake to eat fruits by rewarding some points each time a fruit eaten. The more fruits it gets, the more points it gets. By adopting proper reward policy, the snake will eat fruits as many as it can. As we can see, the snake is almost as smart as human. However, the problem of self-spinning is still unsolved, and it happens from time to time. The fourth one is to combine both encouragement and punishment. It tackles the self-spinning problem without compromising much performance. And this is the average performance of these 4 reward policies. Although the fourth one is not as good as the encouragement only policy, which is the third one. It takes less steps to fetch fruits, which means the snake always chooses shorter or better path. In conclusion, our model is capable of playing snake game and has a really good performance. During experiment, We discovered that similarity between trained models and human beings in terms of game performance with different difficulties. Also, we find out that appropriate reward policy can improve the performance of Snake, but it's hard to mix all the policies together without compromising performance, which means the model with corresponding learning algorithms can be improved in the future. Thank you.